Welcome everyone to the fourth lesson of Area of Study 3. Today we'll be having a look at energy. So it's a pretty long lesson actually. So hopefully you'll be able to get focused and work through this content. All right, what are we going to do? Well, the first thing we're going to do is we're going to look at what is energy. So kind of what does it look like? The next thing we're going to have a look at is what I call the energy bank. Which is all the different types of energy, I guess. We'll have a look at it a little bit more, in a little bit more depth later on. So that'll include work, kinetic energy, gravitational potential energy, and strain potential or elastic potential energy. Those two are the same thing. We're going to have a look at graphs involving energy, and then we've got a few questions throughout. We've also got a pretty long question at the end, kind of an exam style. Okay. What is energy? So energy is commonly thought of in a rudimentary way as kind of the stuff brought in through power lines that you can buy from, I don't know, a company. But within the Area of Study 3, it's a little bit different to that. It refers to the energy produced, used, or conserved within a system of moving parts. And so what that means is that we look at energy in a mechanical sense rather than in an electrical sense. So examples of this is we use some energy provided by the intake of food, so chemical potential energy, to push a shopping trolley around the supermarket. Or we can look at the energy stored in a battery to move an electric vehicle. So the energy bank. So think of the total energy we have in a system. A system can be a situation, for instance, a car, consider that a system, and consider that as kind of like a bank. And within that bank, we can exchange that energy to different forms. So some are in coins, some are in notes, some are in gold bars. One day, we may want all of our energy to be represented in gold bars, but perhaps another time we want it to be evenly distributed throughout all our different types. But the total value remains the same. So with energy, it's lots of different forms, but as part of Unit 3, we're only going to be looking at those things that I already mentioned, so work, kinetic energy, gravitational potential energy, and strain potential energy. So those are kind of the different currencies, I suppose. Right, let's have a look at work. So it's probably the easiest to understand. So energy can be transformed to heat, sound, movement, which is kinetic specifically, etc. So any type of thing that you can consider as transforming potential energy into other types of energy is doing work on something. So you can do that by, say, rubbing your hands together, pulling something with a high frictional force along a rough surface to create some heat. So lots of different examples of work. So typically it comes from the transformation of kinetic energy, but it can also be, for instance, the change from potential to other types of energy. So we think of work usually as doing something to move something else, which is a bit kind of what this formula is about over here. So work is just a way of describing the transformation of energy to another form. So here we have our formula. Work equals force times displacement. And we haven't seen this unit yet so far. So a joule here is kind of newtons times by meters. And it's a representation of for how long can we apply a force, pretty much. So W represents that work done, F represents the force applied, and S represents the displacement. All right, back to question 1. Marty pulls a box along the ground at a constant speed. The frictional force acting on the box is 5 newtons per meter. Calculate the work done by Marty as he drags the box over 10 meters. So it's 2 marks, so you've got 2 minutes to do the question. You can pause the video and come back to it once you finish the question. All right, now that you've had an opportunity to do that question, let's have a look to see what the solution is. So the first thing is to use that formula that we had in the previous slide. Work is Fs, or force times displacement. And here's a little tricky bit. It says over here that the frictional force is 5 newtons per meter, and it's traveling at a constant speed. So what that means is that the net force is 0. So whatever the frictional force is, so too does our tension force have to be, or tension force along the direction of motion. So that's important. Now, this distance here is 3 meters, but this is 5 newtons per meter. So we're going to have to multiply 5 by 3 in order to calculate the total frictional force acting on the body. So what we get is W is 5 times 3 times 10, which is 150 joules. Practice question 1b. Marty is confused as to where this energy goes. Giving 2 examples, outline how energy is transformed from Marty's efforts to pull the box. This is an explanation question, so it may take you 2 or 3 minutes. So have a go, and you can pause the video and get back once you finish the question. All right, now that you've had an opportunity to do that question, let's have a look to see what I would do. So the first thing that I would be looking at is I have to give 2 examples. There's probably, yes, 1 mark for each of those 2 examples that kind of relate to the question. This is what I would say. Marty requires energy to move the box at a constant speed as frictional force acts against the direction of motion. So that's kind of just relating back how energy is appropriate in describing our situation, because we require a force to pull it forwards, pretty much. This energy, stemming from the food that Marty has consumed, is transformed to kinetic energy and then to another type, such as heat or sound, as the box slides across the surface. So the 2 examples it's talking about in the question are going to be heat and sound. So those are our 2 examples. And because outline, I don't really have to explain in any real depth. So I'm just kind of, I guess, outlining how it's transformed. So it goes from his stomach, I guess, he converts the energy within him. That's what happens during digestion. And then we're using that energy to move. So it's kinetic energy. But because it's equated to the frictional force, it has to come out as something else. So it's going to be either heat or sound or something along those lines. It cannot be gravitational potential energy because there's no movement up and down. And there's also cannot be strain potential energy because there's no elastic material involved in this. Okay, types of energy, kinetic energy. It relates to the energy of a moving mass and is often the result of a transformation of potential energy in some form. So it could be chemical, strain, or gravitational. And that formula, which you may have seen from 1-2 physics, is EK equals half mv squared. So EK represents the kinetic energy, also in joules, just like work. M represents the mass of the object, and that's in kilograms, and velocity represents, V represents the velocity of the object, and that's in meters per second. Practice question 2. 2 students, Hannah and Saul, are discussing kinetic energy. Hannah claims that if the mass doubles, then the kinetic energy also doubles. Saul claims that if the velocity doubles, then the kinetic energy would quadruple. With the aid of relevant calculations, evaluate each student's position. This question is worth 3 marks, so you have 3 or 4 minutes. It's an explanation question. Good luck. You can pause the video and get back to it once you finish the question. All right, now that you've had an opportunity to do that question, let's have a look to see what I would do to answer this. So the first thing I would state is the equation for kinetic energy, because both of these statements, both Hannah and Saul, are talking about kinetic energy. So it's always going to be important in some way. So kinetic energy is given by the equation EK equals half mv squared. Pretty straightforward statement. So EK is proportional to, that's what this symbol means over here, V squared. So that when the velocity is doubled, the kinetic energy will multiply by a factor of 4. And Saul is correct. So what that means is that when V becomes 2V, we get V squared becoming 4v squared. I guess that kind of makes sense, because when you square this, you get this result over here. So excusing the handwriting, that's how you get that quadrupling. So that's why it will multiply by a factor of 4. Similarly, it can be said that EK is proportional to M. So by the same argument, assuming that V is constant, then it relates purely to mass. So when the mass is doubled, the kinetic energy also doubles. Therefore, Hannah is correct. So the way that this question would be marked would be the aid of relevant calculations, which is this. That's your relevant calculation. And use that in conjunction with this and with this to allow you to make a statement that Hannah is correct and that Saul is correct. It's kind of 3 marks, 1 for each of those dashes. Yeah, that's pretty much how you'd answer the question. Okay, gravitational potential energy. Gravitational potential energy is the energy that a suspended object contains that equates to the energy required to suspend it. It is often the result of work being done on the object, including when attached to a spring. And we'll have a look at springs a little bit later on. But pretty much all you need to know is that when an object is on top of the ground, and really I should be, to be correct, I would say that it's the distance between the bottom of the object and the ground. So this is our ground over here. The energy required to lift it up would be the gravitational potential energy. That kind of makes sense. But we've got to also remember that it's only the energy that is required to lift it up, not anything that's converted to heat or sound. For instance, pretty much another way of looking at it would be if there was a projectile and you fired it up with a certain kinetic energy, and all its energy was kinetic. The point at which its kinetic energy became 0, in other words, it was suspended, I guess, in the air with no velocity for an instant point in time, that would be its gravitational potential energy. All of that kinetic energy would be transformed into gravitational potential energy. So the formula for that is UG equals mg delta H, where UG is the gravitational potential energy, again in joules. M represents the mass, kilograms. G represents the acceleration due to gravity. Some people just say it's the force due to gravity. It's not, it's just the acceleration, and that's in meters per second squared. And delta H represents the height between the ground and the suspension point. So it's this bit over here that I drew out before. So that is kind of the change in height, or the height above ground if it's being suspended from the ground. Okay, practice question 3. Michelle releases an object from a tall building at 11 meters per second downwards with a gravitational potential energy of 196 joules. Given that the object has a mass of 500 grams, calculate the speed at which the object hits the ground and the distance that it travels. So it's worth 4 marks. You've got about 4 minutes to do this question. It's kind of 2 parts in there. What speed the object hits the ground and the distance that it travels. But I reckon you'll be able to do this. All right, now that you've had an opportunity to do this question, let's see what I would do. First thing is to state kind of, I guess it's a bit obvious, but the total energy, like in our bank, is going to be the sum of all our different energies. So it's going to be the gravitational potential and the initial kinetic energy. So it's going to be 196 plus half mv squared. And then we're going to use this v over here. We're going to use the initial velocity, which is going to be 11 meters per second. We're going to substitute that in over here. Here as well, you can see. So that energy combined is the initial energy, or the total energy. And that gives us 226.25 joules. And we're going to have to use that somehow to calculate the speed at which it hits the ground. So that's exactly what we're going to do. Because we know that all of the potential energy is eventually converted to kinetic energy, then we can say that at the bottom, so at the very bottom where it's almost touching the ground, I guess, all of its energy is kinetic energy, and that's still going to be 226.25 joules. So we can equate the equation for kinetic energy to that, and using this M of 500 grams, so 0.5 kilograms, we can get V squared is 905, which then results in V is equal to 30 meters per second, correct to two significant figures. So again, the maximum significant figures, sorry, the minimum is going to be 2, which is the most that we can give our answer to. That's the first part of the question, John. There's still another part. So at the top, we know that UG is mg delta H. So we know that 196 is going to be 0.5, the mass, in kilograms, multiplied by G, or 9.8, multiplied by the change in height. So we know that the change in height is about 40 meters. So exactly 40 meters. So the change in height between the ground and when it's released is 40 meters, which suggests that the distance that it travels is 40 meters. Okay, Hooke's law. This is kind of a bit of a segue into spring motion, and so it's important that you kind of understand this before we move on to the energy component. So it stems from simple harmonic motion, or SHM for short, and the law reflects that the force acting on the body is opposite in direction, and it increases as the increases in magnitude as the displacement increases. And it kind of explains the motion on a spring. This is the formula, and the negative here is purely directional. It just means that whichever the direction is in H, so whichever the displacement is, the force is going to be acting in the opposite direction. So F represents the strain force in newtons, K represents the spring constant, which we'll have a look a bit more in depth a little bit later, and X, or delta X, represents the displacement from rest length. That's in meters. This is Robert Hooke, the bloke who came up with it, and so the law's named after him, like a lot of things in physics. Okay, so let's have a look at strain potential energy. Strain potential, or elastic potential, is the energy stored in an elastic object when it stretches. So springs and rubber bands are good examples of elastic objects. It's often the result of work being done on the object to move it into a position where the forces aren't originally balanced. So you have to require some kind of force to move it out of its kind of natural position. And the formula for that is going to be UE equals half K delta X squared. Now it's important to note that it's the delta X squared, not just X, because when you get a change in displacement, you have to square the final one and the initial one separately. So UE represents the potential energy of the spring, and that's in joules, and K and delta X are defined as in the slide previous. All right, practice question 4. Zach is playing with a toy car of mass 250 grams attached to a compressed spring with a spring constant of 40.5 newtons per meter on a smooth surface as shown. Zach measures the speed of the car as 6 meters per second after the spring is released. Calculate the difference between rest length and the compressed length. So 3 marks. It'll require a little bit of thought to do this question, but I reckon you can do it. 3 minutes, so you pause the video and get back to it when you're done. Okay, so now that you've had an opportunity to do this question, a little bit of a tricky one, let's have a look to see what I've done. So the first thing is to, again, just like our question before, is find the total energy of the system. That's going to be the potential plus the kinetic, because those are the two that are kind of mentioned in this question. So at the end, all the energy is going to be kinetic. All right, so there's a slight error here. This should be a 6. So we're just going to make that a 6. There we go, it looks like a 6 now. Anyway, as I was saying before, so the total energy is going to be 4.5 joules. Apologies about that little error there. So at the start, the kinetic energy is going to be 0, And so the total energy at the start is going to be completely and utterly potential energy in the spring. So it's going to equal 4.5 joules. And then we can use this formula to calculate the difference between the rest length and compressed length. So we get path times by k, which is 20.25. Then we get the change in x to be 0.11111111, etc., which is the same as saying delta x is 0.33 meters or 33 centimeters. So that's going to be the difference between the rest length and the compressed length, because that's what we've defined the change in x to be. Okay, using a force displacement graph. So this is kind of the next point in our lesson, using graphs to give us results. So the area under a curve, the force displacement graph, like the one that we have on the right here, is going to be energy. It always is, and you can, there is a derivation for it, but there's not really enough room on this slide, so I'm not going to bother try to handwrite it here. But pretty much, you use the work formula, and then you can find that this area under the line is energy. So there's a couple of methods to finding the energy, and often in exams you'll be required to either use the trapezium method or the counting squares method. Those are the methods that are accepted in VCE physics. If you were doing this as a maths course, for instance, in methods or specialist maths, you would be required to use calculus to find it. But they deliberately make it easier in physics, just because that's the nature of the subject. So you can count the number of full squares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all the full squares. And then you've got a few half squares. So that one and that one adds up to 1. And that one and that one adds up to 1, roughly. So it's an approximate method, but it works. So that would be 12 squares. You'd find the energy for 1 square, which would be the difference between here and here, which is going to be 0.2 multiplied by 5, which is 1. So using that method, you'd get 12, or 12 joules, I should specify. So that's kind of how the counting squares method works. And if you want, you can use that as a checking mechanism for the trapezium method, which is slightly more accurate, you could say, because it uses the values that you have. So the trapezium method, you'd take this shape as the trapezium, roughly, and you'd say, well, that's about 25 up there, that's about 5 there. So the difference between height there is going to be 20. Or alternatively, you could say that this is 0.5 and that is 25. So we'll add them together and we'll get 30. So the 20, so you just add the 20, the 5 and the other 5, or you could add the 5 and the 25. Same thing, really. And then you can use your formula for the trapezium, which is A equals A plus B H on 2. So this is going to be A. This is going to be B, and H is going to be along here. That's just the generic formula. So what you get is you get 30 multiplied by H, which is going to be 0.8. Divide that by 2, and if I chuck that in on a calculator, you get 12 joules. So it's the same answer, more like a 2 there. So it just shows you that both of them work, really. That's all. Now, in terms of application, if we had, for instance, instead of force over here, we had weight, and instead of displacement, you had height, you would get the same thing. So the energy would be gravitational potential energy. That's a really common application in another area of study that focuses on that. So that's another option. You've also got force displacement for a spring, and you've got force distance for work. So there's a lot of options, all with the same result of energy. So it's going to be gravitational potential, spring potential, or work. So those are the options essentially for calculating energy using a graph. All right, time for a very long practice question. It's kind of an exam style question, and it's quite common that you get this at the end of a paper, one with a few parts. I think this has 5 or 6 parts to it. It's a good question, I think, and it kind of tests your understanding of the whole lesson. So we're going to have a look at practice question 5A. Of course, this kind of question relies on understanding earlier parts of the question, so we'll make sure that we go through the solutions to each part before we move on. So Ariel is balancing different masses on a spring. The weight, force, and extension of the spring from rest length is recorded in the table below. Plot these points on a graph and sketch a linear line of best fit. Appropriately label each axis, including units. You do not need to include error bars. So typically, sketching questions take longer than the number of minutes, I guess, that's allocated in terms of marks, simply just because you want to be accurate with your sketching. So you may want to get a piece of paper, rule up a rough grid lines, and then attempt this question. So take 4, 5, maybe even 6 minutes. Make sure you address all of these points that you're asked to do, and then come back once you're done. All right, so now that you've had an opportunity to do this quite lengthy question, let's have a look to see what I'll do. Now, I have the benefit of using a computer, so I'm just going to get the graph that I sketched in Excel. Now, full disclosure, this is the best line of best fit you can have, but you really should have in yours something that passes very close to all 5 of the points. So that's kind of how you'd address that. That's how assessors will mark it. They'll go, well, does it look plausibly like it's the best line that you can fit that goes through as many of the points as possible. Now you'll notice that it doesn't exactly go through any of the middle 3, but that's kind of the point. It's never going to be perfectly correlated. So this is kind of the best estimation that you'll get. Now, in terms of labeling or plotting the points, I've literally just taken this table and transposed it. That's all I've done. I have labeled, should erase all this ink, I've labeled weight force in newtons on the y-axis. And I've labeled extension in meters on the x-axis. Now, that's just typically how we do it. You could theoretically switch the axes around, but it's recommended that, well, using this method, we can then find energy if required. Because remember, when we did force displacement graphs, the energy under that was, so the area under that was energy. So this is probably the best way of doing the question. And while it's technically correct, you may find that you lose a mark because it's not the best interpretation. Okay, so 2 questions on this slide. Calculate the gradient of your line of best fit and hence calculate the spring constant of the spring that Ariel used. State the law that you used to reach the value of the spring constant. So there's 3 marks in total, so it should take 3 minutes, although the second question shouldn't take you very long at all. And yeah, there's the table of data here in case you need it, but otherwise refer to your graph. Okay, now that you've had an opportunity to do that question, let's have a look to see how I would answer part B. So from the graph, which I'll just go back here, I need to pick 2 points that I'm going to use. So I'm going to choose those that go through intersections in the grid lines and that are far apart. So kind of the furthest apart so that I have the most accurate value. That's a technique that you generally speaking use to find the gradient because it tends to be the closest to the value that the assessors are looking for. So I'm going to pick 2 points, which are going to be 0.2 and 6, as well as 0.8 and 23.5. Now that is literally on the edge over here. So it's going to be that point there and that point there. So there's not a whole lot more I can do in terms of spreading those points apart. Because I also want them to go through grid lines, which gives me a really good understanding of what the value is at that particular point. Now, the really important part is to use points that lie on your line of best fit. do not use points that are given to you in this table here, unless they absolutely pass through the points, that line. So as a general rule, you will not use the points given to you. You'll deduce them from your own line. So let's pick those 2 points, and we're going to use the formula for gradient that you will have learnt in maths, at least in 8, 9, 10. So it is assumed knowledge, so that you're expected to know how to calculate the gradient. Pretty much it's just take the 2 y coordinates, minus them from each other, and the 2 x coordinates, and minus them from each other. So it's going to be the y coordinates here, x coordinates here, and what we get is 29. And just so you know, the assessors will have a range of values, and they may go kind of 1 or 2 other ways. So probably the acceptable range will be between 28 and 30. So if you get anything between that, you're correct. So this is the second part, I guess, of the first question. So hence calculate the spring constant of the spring that Ariel used. So here I'm using the absolute value function just because I want to make sure that I only really care about the magnitude of the force, not the direction. So I can say the magnitude of F is Kx. So the gradient is K. Because remember, in our graph, we had F and we had X. And so any line here is going to be in the form F equals Kx. And because we want to assume that the y-intercept is going to be 0, and you'll find that in your line of best fit, it will go very close to it, we can say that the gradient is going to be K. So K, the spring constant, is going to be 29 newtons per meter. You have to give the correct unit here, and that correct unit is newtons per meter. Right, and now for the second part, part C, state the law that you use to reach the value of the spring constant. There is only one correct answer, and that is Hooke's law. So Hooke's law is used over here in this formula. So that's the correct answer for part C. Okay, part D. We're moving through the question quite well here. Consider a different spring with a known spring constant of 49 newtons per meter. An object is known to vertically extend the spring by exactly 10 centimeters, at which point it is at rest. Calculate the mass of the object. So there's 2 marks. You may have to use knowledge from another lesson, hint, hint, but you should be able to do this question within 2 marks or so. 2 minutes, I should say. All right, so now that you've had an opportunity to do that question, let's have a look to see what I would do. Now, first thing, because it's at rest, i.e. not moving, it's not accelerating, and therefore we can say that the sum of the forces is 0. And now I can label those 2 forces. When I said that, it's going to be mg, gravitational force, and then pulling up on it is the, using Hooke's law, it's going to be kx. So those are the 2 forces acting on the body, and we can say that when we add those 2 together, but because they're in different directions, it's going to be 1 minus the other, we get 0. So we can rearrange for mass. So it's going to be kx on g, and then we can simply substitute the values in that we already know. So it's going to be 49 multiplied by 0.1 divided by 9.8, which gives us 0.5 kilograms or 500 grams. All right, so I have included the formula and the answers here already, because I think it's important that you know how I would do it, but I also want you to find this formula yourself. So I've included it there in case you want to. I can say scribble all over it so you don't know the answers, just like that. But I really do want you to be able to do this question but understand how to do it. So consider the same mass as in part 5D, and it's pulled down by 20 centimeters and then is released to oscillate about its rest position. Calculate the maximum speed that the mass will travel through each period. Now the answer is there-ish now. 3 marks, so 3 minutes. I have already given you the formula, but I would like you to deduce that formula. All right, so while there isn't enough room on this slide for me to show you how to deduce it here, I can show you if you contact me. It uses an energy approach, so you use the total energy at different points to calculate the maximum velocity. It's relatively straightforward, but it does take up room. So that's why I've left the answers up there before. We can get rid of them now. There we go. There we go. So now we can see, so the velocity at maximum is going to be b times square root of k on m. B is going to be the difference between the maximum and median points. So that's going to be b there, and that is going to be 20 centimeters, because when it's at rest, it's then pulled down by 20 centimeters, and because all energy is conserved, it's going to travel up 20 centimeters. So that's kind of how we use that B. Doesn't really mean anything. That's no reason why it's denoted as B. That's just what I've called it. But the K and the M are the same as normal. So what you get is B is 0.2 multiplied by square root of 49 on 0.5, and you get 2 meters per second. Please, if you want to have a look to see how I got that formula, and you don't really understand, do not hesitate to contact me. For this, I will provide a derivation free of charge. So you're more than welcome just to send me a request through the Air Learners website, and I should be back to you very quickly these days. So please do that if you don't understand, but I would recommend that you ask your teacher, for instance, to work through this formula first. If they don't know, which is possible because some teachers don't, then feel free to contact me. So just to contact me, go to the Air Learners website, look up my name, I'm there. Pretty straightforward, really. So that would be 3 marks. So you probably get 1 or 2 marks for deriving that formula using the conservation of energy approach, which, again, contact me if you need help with that, and then 1 for the answer, pretty much. All right, thank you for your attention. So we covered the following items. We had a look at what I call the energy bank, which includes all our different types of energy within AOS3 or area of study 3. So that's work, kinetic energy, gravitational potential energy, and elastic potential energy, strain potential energy. We had a look at Hooke's law. We did some graph work, and we did a really long question that was part of 5, really. So in our next lesson, we'll have a look at impulse, momentum, and the conservation of energy. Within that next lesson, I will be providing a derivation of that formula. So if you want, really quickly, you can just have a look at there. So thank you very much for your attention. Hopefully you learned something new and that you found this as an interesting lesson. If you want to get in touch, just head to airlearners.com and you can find me on the tutors page. Well, I'm not at the top, but I'm not that far down either. So should be able to find me there. But yeah, until next lesson.